Alright, so we're finishing up chapter 4. We're going to talk about friction. We've got two types of friction that we're going to deal with in this course. We've got static friction and kinetic friction. So we're going to talk about static friction first. Static friction is basically what prevents objects from moving from rest and beginning to slide across a floor. Okay, so friction is the surface, or the force that's actually between two surfaces in contact that's preventing one object from sliding across the other. Okay, so static friction deals with an object that is stationary. Okay, an object that's at rest. All right, you try to push on an object, you push a little bit, and it doesn't move. Right, you push a little bit more, it doesn't move. There's a certain amount of force that you have to apply to an object to overcome static friction to get it moving. Okay, and this frictional force always will apply or will oppose the applied force. Right, so this person is pushing on this crate. The force that's preventing it from accelerating is a static friction force, and it's in the opposite direction. So we've got an object lying on a surface. So we still have the normal and the gravitational force. All right. So while this object is stationary, V is equal to 0, the static force will be equal and opposite to the applied force. Okay. This isn't a third law pair because they're not the same type of forces, right? Each one of these have their own applied force pair and static friction pair. But the static friction will oppose the applied force, and it will be equal in magnitude. Okay, as long as this object is at rest. Okay. So static friction is actually not a constant force, right? So you give an object, you apply a little bit of force on, say, a dresser, right, or a heavy crate. That static friction is going to grow, right? That static friction is going to be larger and larger as you apply a greater force, right? But then eventually, your applied force will overcome the static friction force and the object will accelerate. Alright, so there's a range of values for your applied force where the static friction will meet that applied force. Right, it'll be equal and you won't be able to move the object. It's only with a certain minimum amount of applied force that you'll actually overcome the static friction. Okay, and then it starts to move. Alright. So our expression for the frictional force is going to be mu times the normal force, right? So that kind of makes sense. If I go back here, right, the heavier the object, the greater the normal force would be, the greater the gravitational force would be. And it makes sense from our experience that the more difficult it would be to get that object moving. So the frictional force is directly proportional to the normal force on the object. Okay, and mu is our coefficient of friction. It's unitless. If I divided both sides by the normal force, I get the friction divided by the normal. They'd both be in newtons. It's unitless. Okay, so it's a coefficient of friction, and this object, or this variable here, depends on the two surfaces that are in contact with each other. All right. So this will always be less than 1. Okay, so we'll always get a fractional value or a decimal value for our coefficient of friction. Alright, so that means the frictional force is always some percentage or some fraction of the normal force. Okay, so this is my formula for the frictional force. I have to find out what the normal force is on the object, and then I have to know the coefficient of friction, which is given, or sometimes will be asked for that. So once you finally overcome that static friction, right, once your applied force is greater than that static friction force, the maximum static friction force, there's still friction, right? We still got the two surfaces in contact with each other, but now it's a different type of friction. It's called kinetic friction. Right? The object is now accelerating. There's still friction. There's still a frictional force that's opposing the object's motion. Right? It's going in the opposite direction of the applied force. Okay, but now it's kinetic friction. So We still have the same formula, which is nice, right? It's still mu times the normal force. But for most surfaces, the coefficient of kinetic friction is less than the coefficient of static friction. What does this mean? You have to overcome the static friction, so you have to apply a very, very large force on this object. Once you get it moving, it will take less force to keep it in motion. Alright, because the coefficient of friction for kinetic friction is less than the coefficient of static friction. Right? So in our experience, if we apply a force on something to get it moving, once it starts moving, once it starts sliding across the surface, it takes less force to keep it moving. So it's still the same expression. The thing that changes between static and kinetic friction is the coefficient, which again is often either given or you're being asked to solve for it or something like that. So we'll start with a 1D Newton's second law problem with friction. All right, so we've got another sled. It's on a horizontal surface. So there's a child exerting a 36 Newton horizontal force. So maybe it's pulling it along, okay, but it's an applied force of 36 newtons. Again, just like I think it was our stoplight problem a couple slides back, I'm giving you the weight of the sled, right? 52 newtons, that's the weight of the sled. So I already know the gravitational force. I don't have to multiply this by g or anything like that. So I've got the weight force, cement sidewalk, so that tells me that there's definitely going to be friction. So we're looking for the coefficient of friction between the sidewalk and the metal runners, right? So the child is exerting a horizontal force. So there's an applied force, a frictional force, a weight force, and a normal force because the sled is on the surface. So here is, let's zoom in a little bit. Here is my free body diagram for the sled. Here's the applied force, the gravitational force. I already know it, right? It's 52 newtons. Okay, so I don't have to do this mg. If I'm looking for the mass, right? If I'm looking for the mass, I can use the weight and solve for the mass, right? If I divide both sides by g here, I would get the mass of the sled. But I'm not being asked for that. I might not need it, but just in case, there it is. So I've got the applied force, gravitational force I know, applied force I know. I'll verify that the normal force is equal to the gravitational force like I have in the past, and then I've got a frictional force. So I know the gravitational force. I've got my expression for the frictional force, which is mu, the coefficient of friction between the surfaces, times the normal force. So this means I've got to find the normal force and calculate mu. Okay. So Newton's second law in the x direction. The applied force is in the positive x. The frictional force is in the negative x. So applied minus friction is m times a. In the y direction, I've got the normal force, positive y direction, gravity, negative y direction. Those equal 0. There's no acceleration in the y direction. Okay. So now I know that the normal force is equal to the gravitational force, which is mass times acceleration due to gravity, but I already know that weight force. Okay, so the weight force is 52 newtons, the normal force is 52 newtons right here. Okay, here's my problem. Right, I want to calculate mu. I go back to the problem. Where's the frictional force? I'm not given the frictional force, right? If I had the frictional force, I could use that expression to find the coefficient of friction. I don't have the frictional force. Okay, but if I want to try to solve for mu here, right, if I go back here, the frictional force is mu times the normal force, which I know. So I'm going to take Newton's second law in the x direction, and I'm going to replace friction with mu times the normal force. Okay, but I don't know the acceleration, right? I can't solve this right now because I don't have the acceleration. Constant speed. Okay, so the acceleration in the y direction is 0 because I know the box isn't leaving the surface. But this little phrase right here at constant speed is telling me that the acceleration in the x direction is also 0. Okay, so I'm using this mg. I'm moving this mg around like it's a variable, but I just know that that's 52 newtons. Okay, But in the event that we're given the mass of the object, it's good to get in this habit, you know, and have this expression around. So I solve Newton's second law in the x direction for mu, and I get mu in terms of a, right? And I don't know it. But the problem tells me that the sled is moving at a constant speed, so the acceleration is 0. So this whole term, you could actually cancel it out earlier up here, right? Might make your life a little bit easier. So I recognize later that that the sled is moving at a constant speed. This whole term goes away. So mu, in this case, is the applied force divided by the normal force. All right. So if I go back up here, right, friction is mu times the normal, which means mu would be friction divided by the normal. I knew the normal force. Since the acceleration in the x direction is also 0, the frictional force is equal to the applied force. So I know both of those. Right? 36 newtons over 52 newtons. I'm getting a fraction, something less than 1, which is good. Mu is equal to 0.7. So that's a high coefficient of friction. Right? If I picture this problem, I got a sled with like metal blades on the bottom of it sliding across the sidewalk. Very high coefficient of friction, going to be very difficult to slide it across. Alright, so next example, I've got another block that's sliding across a rough surface. Now it's got an acceleration of 1.25 meters per second squared, but it says it slows down. So picture you're pushing a block and then you let go of it, right? And then it slows down and comes to a stop. So we're looking for the coefficient of friction between the block and the surface. Again, the difference between this problem and the previous problem is I'm given the mass instead of gravity, or the gravitational force. No big deal. I don't have an applied force. Right? I'm picturing this block as if it's sliding. It's got an initial velocity, and then it's accelerating in the negative x direction, and it slows down to a stop. So my free body diagram for the sliding block is very similar to the sled, except I don't have a child pulling it. So I still have normal, I still have the gravitational force, but now the only force in the x direction is the frictional force. Okay. So in the x direction, the frictional force is equal to the mass of the crate times the acceleration. Just like the previous problem, in the y direction, the normal force is equal to the gravitational force. All right, not always the case, so I write out Newton's second law in the y direction just to be sure. The normal force is equal to gravity. I have the gravitational force. I've got the mass of the crate, acceleration due to gravity. I've got the normal force, 13.72 newtons. So I have the acceleration. Okay. I'm going to substitute the magnitude of the acceleration here, right? See how I wrote friction as mass times acceleration? This would actually be a negative sign in front of the friction, the frictional force, okay? And those negative signs would cancel out. So I'm just going to substitute a positive acceleration here because I'm looking for the magnitude of the frictional force, basically, okay? So I've got the acceleration, I've got the mass of the object, so I could calculate that frictional force. But I'm not being asked for the frictional force, I'm asked for the coefficient of kinetic friction. So the frictional force is mu times the normal force. I'm going to take Newton's second law in the x direction, substitute mu times the normal force in for the friction. I get mu times the normal is the mass of the crate times the acceleration. So I can solve this for mu. I have the normal force calculated already. I've got the mass of the crate. Again, I'm substituting the magnitude of the acceleration in here because of this negative sign issue. Divide both sides by the normal force. Mu is mass times the acceleration over the normal. And I substitute my values in, and I get a coefficient of friction of 0.13. Okay. So very, very similar to the child pulling the sled. The only difference is we have an acceleration in the x direction, which we're given, and we don't have an applied force in the positive x direction. Okay, so friction is mu times normal. We're just adding another equation into our Newton's second law process and another force. Right? Now this frictional force is always going to oppose the motion of the object. Okay, this object was going in the positive x direction. Friction is going to oppose that motion. It's going to go in the negative x direction. Okay. So that may change depending on the direction of the object. So just be on the lookout for that. All right, so let's sneak a two-dimensional force in here. I got another box being pulled across the surface. Okay, I've got the mass of the box. I've got the applied force. Right, I've got the applied force, but that applied force is acting in both the x and the y direction. So think of the kid pulling the sled again, but the kid's a little taller than the sled, so it's pulling up and to the right on the sled. So there's a two-dimensional force, two-dimensional applied force on this box. I'm given the coefficient of friction now. Given the coefficient of friction, I'm looking for the acceleration of the box. All right, so I've got a mass, I've got an applied force, I've got a coefficient of friction, so I could probably find the frictional force using Newton's second law. I've got theta, I've got the angle of the applied force, so I'm going to have to resolve that into x and y components. I'm going to start off with a free body diagram. Gravitational force, normal force, I've got a frictional force. I was given the coefficient of friction, so I'm going to assume there's friction. Okay. Then I've got the applied force in the x and the y direction. So the first thing I'm going to do, I'm going to split the applied force up into x and y components. Fa cosine theta is the x component, Fa sine theta is the y component. I can calculate both of those. Right? I'm going to run through it with you know, my expressions and everything first. I'm going to wait till the very end to substitute my values. That's good practice. But the frictional force is mu times the normal. Here's the issue. We haven't dealt with this too often, but we've got another force in the y direction. Other than the normal force and the gravitational force, we've got another force. So when I write Newton's second law in the y direction, that's why I've been doing it this whole time. Right? We've been getting similar results for Newton's second law in the y direction. But this is going to be different. All right? That's why I've been writing it out every time. So Newton's second law in the y direction says that the normal force is in the positive y, the gravitational force is in the negative y, right? We've got normal minus gravity as we normally do, but we've got another force in the y direction, F applied in the y direction, all right? So the normal force plus Fa sine theta, that's my y component, minus the gravitational force is equal to 0, right? We're assuming that the box is not leaving the surface any time during this problem. All right, so the net force in the y direction is 0. So I'm going to need to solve for the normal force because I'm going to need the frictional force to find the acceleration of the object. Okay. But I can calculate this. Right? I've got the applied force, I've got the gravitational force, I've got theta. All right, so I'll be able to calculate the normal force when I need it. All right, Newton's second law in the x direction. I've got the applied force in the x direction, the x component of the applied force. The frictional force in the negative x direction. That's equal to the mass of the box times the acceleration. I'm being asked for the acceleration, so I'm assuming there is an acceleration. All right. So the applied force in the x direction minus the frictional force is the mass times the acceleration in the x direction. So I'm substituting this in for the x component of the applied force right here. And I'm substituting mu times the normal force in for the frictional force. So I'm going to solve Newton's second law in the x direction for the acceleration. And I'm pretty sure at this point that I have everything I need to calculate the acceleration. All right. So divide both sides by the mass of the box. So the acceleration is Fa cosine theta minus mu times the normal over the mass of the box. I need the normal force, right? I've got Fa, I've got theta, I've got mu in this problem. Yes, it's 0.1. I've got the mass of the box, 50 kilograms. I need the normal force. So I'm going to take Newton's second law in the y direction, solve it for the normal force, calculate it. So I've got to add F sub g to both sides, subtract Fa sine theta from both sides, and I get the normal force is gravity minus Fa sine theta. Now this kind of makes sense, okay? So normally normal was equal to gravity, right? Normal is a little bit less than gravity right now. See how it's gravity minus some term? That's because something is pulling up on the box. Right? Pulling up on the box. So it's decreasing the normal force. Right? It's decreasing the force that the surface is applying to the box because something is pulling up on it. Alright, so that makes sense. So calculate it. Right? Substitute our values. Mass, G, F applied, theta. I get a normal force of 427.5 newtons. Now I've got everything I need to plug in here to solve for the acceleration. F applied, theta, mu, the normal force, mass of the box. I get a positive acceleration, so that's good, right? The applied force is overcoming the frictional force, so there's a net acceleration of 1.3 meters per second squared in the positive x direction. Okay. Same process, we're just adding a new force. We've got a new expression for that force that's dependent upon the normal force. Alright. Still writing Newton's second law in the x direction, Newton's second law in the y direction. Use algebra to solve for what's being asked for. Substitute the values. Alright, so let's do a couple of incline problems. Do a couple incline problems. I'll pause it and I'll make a second video for the last couple friction problems. Okay. Alright, so I've got a skier going downhill. I've got the mass of the skier and I've got the incline. I've got the angle of incline. I'm going to draw this a little bit differently. We have, you know, freedom with our coordinate system to kind of make our lives a little bit easier. So I'm going to draw it a little bit differently, but you know, it's really up to you how you want to set up the problem. So the person is skiing down a hill. The slope of the hill is 37 degrees. I've got the coefficient of kinetic friction. The skier is moving, so the coefficient of kinetic friction is 0.15. So we're looking for, and this gives me a hint that I'm going to need a little bit of kinematics here, right? How fast is a skier going 5 seconds after starting from rest? So I got a v initial of 0, I've got a time interval, and I've got a v final, right? So I can use a kinematics equation to find v final, but I need the acceleration. All right, so this is a very nice problem where we combine Newton's laws and kinematics in one problem. So let's use Newton's second law to find the acceleration, and then use kinematics to find the velocity sometime later. So we're on an incline. I'm just going to flip it around so that down the hill is the x direction, or is the positive x direction, right? So I'm drawing this a little bit differently. Down the hill is the positive x direction, up the hill is the negative x direction. All right. You can flip it around. You'll be dealing with some other negative signs. It's no big deal, but as long as you're consistent, you should get the same answers. All right. So I got mass, angle of incline, mu, my kinematic stuff here. What am I looking for? All right. Free body diagram. I've got the normal that's always perpendicular to the surface. I've got gravity acting towards the earth, but I've been studying my inclined plane problems, and so I remember that the gravitational force in the y direction is Fg cosine theta, and the gravitational force in the x direction, down the incline, right, is F sub g sine theta, right? This was negative in our problems before because I drew the incline differently, and I said down the hill was the negative x direction. No big deal. It's the positive x direction. When I write Newton's second law, I'll give everybody signs based on whether they're, you know, acting positively or negatively. Got the friction is opposing the motion. Skier is sliding down the hill. Friction is opposing the motion. Friction is acting up the hill. Newton's second law in the x direction. mg sine theta minus the frictional force is equal to the mass of the skier times its acceleration. F net in the x direction, mg sine theta minus friction, is mass times acceleration. So I'm solving this first for A, right? I need the acceleration first, so I'm making a nice expression here, right? In terms of the mass, g, theta, and the frictional force. What's the frictional force? We always say it's mu times the normal. Okay. So let's substitute that in. Mu times the normal. I got mu, that's great. Where's my normal force? Don't know. I use Newton's second law in the y direction to find the normal force. Newton's second law in the y direction, positive y is the normal. Mg cosine theta is in the negative y. So normal minus mg cosine theta, right? Not just mg. Normal minus mg cosine theta is equal to 0. Again, no acceleration in the y direction. So the normal is mg cosine theta. So come over here, substitute mg cosine theta in for your normal force. I'm going through a lot of this, right? A lot of people get uncomfortable with this process, using the variables, substituting equivalent expressions, all that stuff, right? You're just dying to plug numbers in. Wait until the very end. It's actually a lot nicer in this problem, all right? So I substitute mg cosine theta in for the normal force. I'm looking at all three of these terms. Okay, I'm looking at all three of these terms, and I see that 1, 2, 3, every term in this expression has a mass in it. Okay, so I can cancel that out. That's a common factor, right? It has to be in every term. Just a little FYI reminder from our algebra days, okay? Mass goes away, okay? So now I've got g sine theta minus mu g cosine theta. All right, so that helps me. I have to substitute less opportunity for calculation error. All right, substitute g, theta, mu, and you get an acceleration of positive 4.7 meters per second squared, which is good because I said I want the skiers, I want down the hill for the skier to be the positive x direction. All right, so I'm getting a positive acceleration down the hill. Okay, it says how fast is the skier going, so you're going to get a positive final velocity. Down the hill's positive x direction, you're going to get a positive final velocity. Use this kinematics equation to look for v final. V final is v initial. Oh, that's right, starting from rest. So I know v initial is 0 plus a t. I've got a final velocity of 23.6 meters per second. Practice this. Alright, practice this right here. Substitute your expressions in. Use Newton's second law. Solve for the missing variable in terms of everything you know. If there's something in that expression that you don't know, there's another equation that you've made where you can solve for that missing quantity in terms of things that are given. Substitute that in first. I'm looking for common factors that I can cancel out, alright, when I'm able to, so I can substitute fewer values in. Alright, make my calculating life easier. Okay, so good practice to be in. I'll also say, like on a problem, I'll say derive an expression for the acceleration in terms of, you know, these three variables. Alright, so be comfortable with this type of problem. If I just say mass theta mu, okay, mass theta mu. I don't give you numbers, but I give you variables, right? I'll give you numbers later and then you can plug them in. But be comfortable getting to this step, right? Derive an expression for the acceleration of the system using only variables that you know. We all know what g is. We were given theta, we were given mu. Okay, so good practice. Good practice. It's not always about the numbers. Alright, so I think maybe my scan got a little cut off here, but I think we can make it with this next problem. I think we got another skier, right? But now the skier is going up an incline, and it's being pulled up the incline with a rope, right? So it's like a water skier being pulled by a boat, and then they hit a ramp, right? And they're holding on to this this rope, and it's pulling them up the incline. So there's a tension in the rope of 512 newtons. So we've got the applied force, we've got the mass of the skier, we've got the angle of the incline, coefficient of friction. What's the skier's acceleration? Newton's second law problem. I'm going to say now I'm drawing the picture, so up the hill is the positive x direction, right? So I've got the applied force acting in the positive x direction, the frictional force acting in the negative x direction. Guess what else is acting in the negative x direction? mg sine theta. I still have to account for gravity here in this inclined plane problem. So in the x direction, I've got F applied in the positive x, friction, and mg sine theta in the negative x. In the y direction, I've got the normal, and I've got mg cosine theta in the negative x. All right. Friction is mu times normal. What do I know? Mass of the skier, coefficient of friction, the applied force. I'm calling it F applied. Excuse me. It was called a tension, right? So if you go through this problem, you use T, that's fine. But it's 512 newtons. All right, Newton's second law. This is Newton's second law in the x direction. All right, Newton's second law in the x direction. F applied is positive x, friction, negative x, mg sine theta, negative x. So applied minus friction minus mg sine theta, mass of the skier times the acceleration. That's what I'm being asked. All right, that's what I'm being asked. So I know friction is mu times the normal. I know the applied force. I know all this stuff, right? So I know these numbers here. I'm looking for the frictional force. Mu times the normal, not given the normal force. I have to write Newton's second law in the y direction to find out what the normal force is. Normal, positive x or positive y, mg cosine theta, negative y. So the normal is equal to mg cosine theta. Again, no acceleration in the y direction. So I've got an expression for the normal force. Okay, again, I'm being a very good physics student here. I'm substituting my values before I plug my numbers in, or substituting my expressions in first. So I got an expression for the normal force in terms of things that I know, mg theta. So solve Newton's second law in the x direction for the mass. Not too bad, just got to divide both sides by m, and the acceleration is this expression right here. It's still in terms of the normal in terms of the normal force, which I don't know, so I'm substituting mg cosine theta in for the normal force. So now I've got the acceleration is F applied, which I know, minus mu mg cosine theta. Right? Mg cosine theta, that's my normal force. Mu I know, m I know, g I know, theta I know. That's great. Minus mg sine theta, that's the gravitational force in the y direction, or excuse me, the x direction, which I know all of those terms, divided by m. Now I'm ready to plug in all my values. I know F applied, mu, m, g, theta, m, g, theta. All right. Be careful, I drop this mu sometimes, right? See how you got a lot of mg's and thetas, right? I forget where this mu goes sometimes, so just be very careful with that mu. All right. Divided by the mass of the skier, and I've got an acceleration. I calculate this acceleration positive 3.2 meters per second squared. All right. So this applied force, or this tension in the rope, is overcoming friction and this component of gravity. So the skier is accelerating up the incline. All right. So I've got one more problem, and I will make a quick video on this because this is a pretty involved problem, right? And I already feel like I'm kind of over on my time here on this video, so I'm going to make one final friction video, solve this problem, get started on chapter 5, get those uploaded as quickly as I can. Alright, hope everybody's having a good weekend if you're watching this, and see you in a little bit. Thanks.